He's going through a lot.
Okay, so let's go ahead and get started.
That took 8 hours.
So I saw that everyone took the exam, which was good. I started grading them. I hope to finish tomorrow. And then you'll have again 1 week if you want to resubmit any incorrect. Okay. So today, one of the topics that we're starting is on quantifying bacterial growth and learning how to do serial dilutions. This includes how to determine the dilution in terms of like what volume of culture to mix with what volume of diluent to make a 1-to-4 dilution. So there is a homework on this on Canvas and it's due on Tuesday. If you get stuck at all, if you need any help, please feel free to reach out with myself or Rich, okay? Chapter 13 material, now that you are done with the exam, you should be moving into chapter 13 material. This is due in 1 week. Okay. And then next Thursday, you also have lab quiz 3. Please keep that in mind and don't leave that chapter 13 material until the last minute. Okay, so first topic, we are going to analyze our transformation results. So we want to determine whether or not transformation is working. So we have MH.
Did you get me? I've been trying to work on an open.
What's sitting? 12? 13?
13.
Oh.
You just look so
All right,
beautiful.
so just to
What'd you do
recap,
today?
in case
Just
this
for
isn't fresh in your
you
mind,
came to work or it
remember
was just
that
for
we
school?
started with E. coli, and we had E. coli in 2 different tubes, okay? One of the tubes, which we marked with a plus sign, we also added in the P. blue plasmid. The one that we had a minus sign, we didn't give the plasmid to, so it was a control. The P. blue plasmid had 2 key genes on it. One was an ampicillin resistance gene, and the other was a LAC-Z gene. So hopefully the ampicillin resistance gene is pretty apparent at this point what it provides for the cell. But the LAC-Z gene, remember that this is a gene that codes for an enzyme that converts X-gal into a glue product. So if this gene is present in a cell and expressed, and there is X-gal in the agar, as we would have with the LBAX plate, then you should see blue colonies. Okay? So if we start with just the LB plate, did you have growth on LB?
Yes.
For which samples?
Both.
Both. Okay, so you should be marking your results as yes or growth. Okay. So what does this tell us? Why do we do this? Why do we even bother having it grow on plain LB? It tells us what? Verifies what? Yeah, they're viable cells, right? So if we didn't do this and all the other plates, we had no growth, well, we would first ask the question, well, were the cells healthy to start? Okay, so this confirms, yes, we have healthy cells. We didn't have the water bath too high, we didn't kill them when we put them in there for heat shock. Okay. Next, we have the LB with ampicillin plate. Did you have growth, and if so, which ones? You didn't have growth on either.
On which ones?
I have growth
On which one?
on the positive. LBA.
Did anyone have growth of the minus?
No.
No.
The positive, I have 2 colonies.
You had some colonies, and
2.
what color are they?
Cream.
Yeah, I have white.
You had a little bit?
Small amount right there.
Did you expect growth of your positive strain on the LBA? Yes. What would that tell you? How could it grow in the presence of ampicillin?
They have the ampicillin resistance gene from the,
From the plasmid, and so what worked?
transformation.
Transformation, yeah. can put white or cream. And so, hopefully this makes sense why there's no growth for the minus. We never even gave it a chance of taking in that plasmid. So it shouldn't have ampicillin resistance. Okay. So,
It had growth because.
Transformation occurred, so it was ampicillin resistant.
Occurred. And then what did you say?
It was ampicillin resistant.
alright, so those of you that have growth of the plus on LBA, compare the amount of growth of that to your plain LB. So just those of you that didn't,
What are we comparing? The
LB.
LBA?
To the LB.
LB negative or positive?
So LB should be on both.
Yeah.
Right?
Yeah. The LB both of them.
Yeah.
And you're comparing the LBA to it.
Yes.
How can you even compare these? They're completely different.
Take a picture of the board for her after.
I have two colonies there. That's
Yeah.
it.
alright, is the relative amount of growth the same?
No.
Which one is less?
LBA.
Yeah.
LBA positive.
So, remember that the only way that you could get growth of the positive strain in the presence of ampicillin was if those cells were transformed. So imagine that if you started, let's say, 1 million cells, added in the plasmid, some of them successfully take it up, some of them don't. The ones that don't cannot grow in the presence of ampicillin. And so because transformation is not 100% efficient, this explains why you see such less growth in the presence of ampicillin. These are only the transformed cells, okay? Not all the bacteria that you start with will be transformed, only a fraction of them are successful.
So the only way
Whereas on just the plain LB cells, that should, LB plate, that should be nearly all of the cells that you started with. Okay. All right, how about LB with ampicillin and XCAP?
the one with the blue colony?
So hopefully, again, you have growth that is likely is the same relative amount as in the presence of ampicillin.
Yep.
You should have no growth for the minus strain. Never had that ampicillin resistance gene. And furthermore, the growth of the positive strain should be blue. Did anyone get any white column?
With the white.
Did you guys not get growth?
Yeah, real quick. No growth on the negative because no ampicillin.
Transferred?
Right. I literally got one. How many did you get?
3.
3.
4.
Oh, 4.
You
Ours
did
are like
so
bunched
many.
up together.
Let me see yours.
I
1.
just got one. Ooh.
She thought we did something wrong on the minuses.
Oh.
At first, when we first got them, she's like, did I scrape them? And she did them, and she was like, did I do it?
Yeah, we'll talk about that in a second.
I got one.
One, okay.
Better than none. Oh, wow.
So just to show you a lot of growth. Yeah, great.
That's a lot.
I think you also have a white colony, right?
Oh, actually,
that
I
your
might
phone?
have one right next to the blue one.
No, I don't
Yep,
think
I see
so.
it.
Yeah.
And you
I don't
don't?
see it.
Why did ours only get a few and this one got a bunch?
I don't know.
Is that somebody's from in here?
Yeah.
No. I think this is the last class. Not sure.
That's a lot of growth.
That's why I'm wondering why so much transfer on that one and not this one.
I got one of the white colony. I just didn't see it before. Alright, I need to get my phone.
one
on its own.
that has like the thicker middle that just isn't blue.
Gotcha.
I don't see no white ones.
No, she says no.
Okay.
She thought she said no.
Okay, so those white colonies are called satellite colonies. They're actually small colonies of cells that are not transformed. They actually never took up the plasmid. But what happened is that they were able to survive long enough until the transformed cells that do have ampicillin resistance gene, they release, let's say, an enzyme. They secrete the enzyme that breaks down the antibiotic in the agar, allowing those colonies to grow. Even though they are not transformed, they do not have the ampicillin resistance gene. They can still grow in the presence of ampicillin because the ampicillin in that small region right there, right around the blue colony, is already destroyed. And that also explains why they're white. Because they're not transformed, they also don't have that LAC-Z gene. And so they have no way of converting the X-gal into a blue. Okay. Any questions on this? So those of you that didn't get this to work, it's not uncommon, so don't fret about that. It might be, this one that I have is actually from a different class, and it might just be that, I don't know, that they had it incubating longer, that the cells were healthier, I don't know. Okay. Know that you should record your own results in your discussion. If it didn't work, you should know that this is a unique result, that it wasn't expected and why. And you should also be aware of what you did expect and why. Okay?
I just have a question. If we have like those 5 little colonies, is that still successful? Because we do have like some, like, you know, like, we have like,
Yeah.
these little ones, that's still successful?
Still successful, yep.
Okay.
Yep.
Thank you.
Okay. Any questions on this? Okay. So you can move those aside. We are going to move on to the next topic that we'll start. In this lab, we want to determine how to quantify the amount of cell growth or cell density in a stock culture. So I have up here an equalized stock culture. And I want to determine what's called the cell density. And cell density could be either cells per volume or colonies per volume, okay? Now, if I were to just take this and take a little sample of this and add it to an agar plate to like streak it, I would need to know how much volume I am adding on. So I can't just take a loopful, right? And plus, it's likely so concentrated right now that even if I did that, the amount of colonies would be too numerous to count. So what we do is we prepare multiple dilutions. We plate different dilutions and hope that at least one of those plates are countable. We keep track of how much we diluted and how much volume of that dilution we're adding to the plate, because those will both be taken into account when we calculate the density, the cell density. And again, all of this, the goal of this is to go back and determine the concentration of that original stock culture. We'll use the concentration of our dilutions and kind of back calculate the concentration of our original stock culture. So we're going to prepare multiple dilutions. A very quick way of preparing multiple dilutions at once is called a serial dilution. Okay. So what we're going to do is you have on the side bench, we have tubes of sterile water. You're going to collect 7 tubes, and you can line them up in a line either in your long blue rack, or you can put 2 blue racks together. On the side, you're going to label the dilution, which we're going to work through in a minute, and then what we call serially dilute them. So I have the equalized stock culture up here. What we're going to do is you'll first bring up this first tube to me with 9 mils of sterile water. I'm going to make your first dilution by taking 1 mil of E. coli and adding it to 9 mils of sterile water. when you take 1 mil and add it into 9 mils, so you have 10 mils, that is a 1 to 10 dilution. The 10 represents the total parts. So this will be 10 total parts when I add that. My culture is one of those 10 parts. This is different than a ratio. So think of how people use ratios in cooking.
That's what I
Where
was
you
just
say
gonna ask.
sugar to flour of a 1-to-2 ratio. That is saying 1 part sugar, 2 parts flour. So 1 cup sugar, 2 cups flour. That's very different. This is saying of the 10 parts, one of those 10 parts is my culture. Okay? All right, now I mentioned that serial dilution means making multiple dilutions quickly. So you take 1 mil, you add it into this 9 mil, you mix it up and down, that gives you a 1 to 10 dilution. Now, you extract 1 mil again, same volume, into 9 mils. This 1 mil is already at this dilution. So since you have 1 mil at 1 to 10, and you're further diluting it 1 to 10, this is 1 to 100.
So you're adding a 0 every time?
Do this again.
That's what I'm about to see.
Doing the same dilution every time.
Is it just 1 to 100 and then 1 to 1,000 and
Yep.
so on?
Yep. Right, 1 to 1,000, 1 to 10,000, 1 to 100,000, 1 to 1 million, and 1 to 10 million. Now this can, as we get more and more dilute, this can get cumbersome to write. So, the other way that you can represent this, think of this 1 to 10 as a fraction. You can also write this as 10 to the minus 1. Okay? This minus 1 means that this is inverted, meaning you flip it so it's 1 over 10. 1 to 100, if you write it as a fraction, 1 over 100, that is 10 to the minus 2. You can also think of this number here, the exponent, representing the number of zeros, if you want to double check. Okay, so 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, and 10 to the minus 7. That is your dilution. And so when you select 7 tubes over there and you need to label them all, I recommend, with your lead pencil, of course, that you label the white part with your lead pencil 10 to the minus 1, 10 to the minus 2, all the way up to 10 to the minus 7. All right, the other thing that I quickly want to cover is that, so what we're going to do is we are going to prepare these 7 dilutions. These last 2 dilutions we are going to select to use to prepare 2 plates. So one will be at a 10 to the minus 6 dilution, the other one will be at a 10 to the minus 7 dilution. We're hoping, come next week, when we look at these plates, that one of them is within countable range, which is more than 30 colonies, less than 300. Okay? We're hoping at least one of them is that. So let's say we're able to count one of these, and we say, okay, that one was a 10 to the minus 6 dilution, and I used 1 mil of that. Well, if I can determine the concentration of colonies on that, for that dilution, remember my goal is not to determine the concentration in that dilution, but to determine the concentration in the stock culture. So, if you think of this as being tenfold diluted, you can think of this as having tenfold less cells or colonies than the stock culture. Which means that whatever concentration you determine here, you would have to multiply that number by 10 to get the concentration here, right? This is tenfold less. Whatever concentration you determine here, you would have to multiply by 100 to get the concentration in the stock culture. So that factor factor that you're multiplying by is called your dilution factor. So this is the number that we will multiply our cell density up by to determine the actual concentration in the original stock. So whatever we determine is the concentration in this dilution, we'll multiply it by this dilution factor to get the concentration of the stock. Now the dilution factor, you can think of as simply whatever's in the denominator or whatever's on the right-hand side if you write it this way. So the dilution factor for this first one is 10. The next one is, you can write it 100, which is the same as 10 squared. If you're not comfortable with exponents, you can just write it out. Okay. The dilution factor for 10 to the minus 3 is 1,000. Again, the 3 represents 3 zeros. It's the same as 10 to the positive 3. The dilution factor for 10 to the minus 4 is 1 with 4 zeros, 10,000, or 10 to the positive 4. So keep going
It's
like
the
that.
opposite. I feel like I'm taking in so much right now.
So this dilution factor will come into play more next week when we're calculating the concentration, but you will also be asked to determine this on the homework. Okay. Any questions on any of this? Okay. So let me just flip this so you can see.
I'm gonna just rewatch it later.
So the first thing, I forgot to write.
I think that's so cool.
So you're going to prepare all these 7 dilutions. Once you have all the dilutions prepared, your 10 to the minus 6 dilution, you are going to use, as well as your 10 to the minus 7. From the 10 to the minus 6, you are going to take 0.1 mil and add it to a plate. So it's 10 to the minus 6, 0.1 mil. You're also going to repeat this with 1 mil. So 10 to the minus 6, 1 mil. And then do the same thing for 10 to the minus 7. First, take 0.1 mil, put it on a plate, and then do the same for 1 mil.
So we're doing it to plate 5, 6, and 7.
I'm sorry?
We're doing it to which plate?
You prepared the 7 dilutions, with the last 2 dilutions is what you're preparing the plates with. So the first step in this instruction is you're going to get 4 empty dishes from over there. I'm going to show you how we're doing this in a second. On the bottom side, you'll label 1, 10 to the minus 6, 0.1 mil, your initial and date. The next one, 10 to the minus 6, 1 mil, initial and date. And then the third and fourth one like this. You'll collect 7 tubes of sterile water, label them with those 7 dilutions we talked about. You'll bring up your 10 to the minus 1 dilution up here, and I'm going to start you off by giving you stock culture into that first one. You bring it back to your desk, and then you're going to perform the serial dilutions. Now for the serial dilutions, we have these serological pipettes, and so proper aseptic technique is to not reach in and touch them all, but to try to shake one out so that you only touch one at a time. Keep them covered if you're not using them. Remember with the roller, it's best if you roll it a little bit, it gives you a little pocket of air to kind of push out what's left. Also make sure that you are comfortable with the graduations before you start measuring. Remember that to measure 1 mil, you actually go up to 0 here. It does it opposite. So once I give you the equali, then you will pipe it up and down, or you can kind of swirl it a little bit if you wanna try to mix it that way. Then aspirate up to the 0 to get 1 mil, put it in the second tube, the 10 to the minus 2, swirl it or pipe it up and down, extract up to the 0 for 1 mil, go into tube 3, 10 to the minus 3, and keep doing that. Okay. Once you're done with these can go, and you all have these white metal bins with some bleach solution on your bench, and you can put them in there for disinfection and get a new one. Then with your 4 plates, just so I show you what you're gonna do. So let's say I have all 7 of my dilutions prepared, and this is my 10 to the minus 6 dilution, 0.1 mil, okay? Again, get familiar with the readings, because 0.1 mil, you have to go up to the 0.9 mark, right? Because you do, 1 minus 0.9 is 0.1, so it's that first graduation right there, it says 0.9. So I would measure, let's say, I'm pretending that this is my dilution. I would measure up to that 0.9. I'm going to add it directly to the middle of my plate. There's nothing on this plate other than that dilution, okay? Get rid of this. Then, come over here, and there's a tube of agar that you add on top of your dilution. So I add it on top of my dilution. I swirl it around, and then I put it off to the side to solidify. This is called the pour plate technique. Instead of pouring agar and then spreading culture on top, you add the dilution on the bottom, then add the molten agar on top and mix it. One advantage of this is you can add larger volumes, such as 1 milliliter. Mix it in. On next week, when we look at this, we'll see that some of the growth happens at the surface layer, but some of it happens in the agar too, and it looks quite different. So that's how we're preparing our 4 plates. Again, once you have all 4, just let them solidify. You have to wait a bit longer this time to let them solidify. And then eventually we'll put them in the incubator